All right, folks, so we're going to start on page 1 of the review, and we're going to start by outlining and kind of diagramming our process that we use for linear programming. So down at the bottom, we're going to kind of do a step-by-step process that will work not only for these general linear programming ones, but also for the story problems. So step 1 is going to be writing the inequalities. Also defining your variables. So define variables and write the inequalities. Remembering that at most is a phrase that means less than or equal to, and at least means greater than or equal to. When you are writing those inequalities, you're going to look for totals and like units to figure out how those will be structured. So there's step number 1. Now, we don't have to do step number 1 for these problems above. We're already given the inequalities and the variables, so this is mainly for the story problems, but this flow will work for these top problems as well once we get into the graphing part. Number 2, we define our objective function. The notation for the objective function is f of x, y. And I would put a little note by that because that notation you need to memorize. So that was a big thing on the first test. It's going to be a big thing on the final as well. Your objective function is whatever you are trying to maximize or minimize. And a lot of times it has to deal with money. Whether it's profits or costs, objective function is money. These are all going to 1.1 and 1.2 linear programming. Number 3, after we have defined our variables, written our inequalities, and written our objective function, next we are going to graph the lines. Now, to graph those lines, there are 2 different formats that our equations can be in. They can be in slope-intercept form, or they can be in standard form. So slope-intercept form is the one we are a bit more used to, the one we've used in the most recent chapter with finding the intersection of a line and a quadratic. So y equals mx plus b, where m is our slope, and b is our y-intercept. And then our second method of graphing we haven't done probably since this chapter, and that is standard form for a line. ax plus by equals c. Now, reminder that when we first did this in linear programming, some of you all were like, I'd rather just do slope-intercept form all the time. Standard form is going to be useful because those intercepts oftentimes become our x and y intercept points and our vertices of our feasible region. So in order to graph using standard form, we use the cover-up method. And how we do the cover-up method is we plug in 0 for y and figure out what the x-intercept is. And then we plug in 0 for the x to figure out what our y-intercept is. And I'll be demonstrating this on a problem for you, but this process is going to be helpful. Now, from those 2 methods of graphing, yeah, I'll send her in. You can go ahead and go. Now, after we've graphed the lines themselves, our next step is to do the shading. So that's the difference between just graphing a straight up line and graphing an inequality. Inequalities are going to have shading, and how we determine the shading is by doing a test point. We want to try to do 0, 0. It's usually our best point of plugging in. The only time we can't is if the line goes through 0, 0. So this is going to determine our teeth. If you remember, the teeth show the direction of the shading. Now, once we have found the teeth or the direction of the shading for all of those different inequalities, what that leads us to is our feasible region. Which is our shaded solution. Now, the feasible region represents all the possible coordinates that will work. But what ends up maximizing or minimizing our function is the vertices of the feasible region. A lot of times your vertices will be exact, usually with the x-intercepts or the y-intercepts. But if they are sketchy, we use substitution or elimination. So substitution or elimination for sketchy vertices. Does anyone remember what we do with the vertices once we have them? Once we have, let's see, those xy coordinates, we are then going to plug them into our objective function. So we're going to take those vertices and we are going to plug them into our objective function for x and y. And that will give us some maximized or minimized amount. So after we find the vertices and plug them into our objective function, that then takes us to the solution. And make sure with the solution, you include your units. So that kind of gives us an outline of what we're going to be doing with these linear programming problems. So I'll leave you guys to do the first two. We're going to go ahead and walk through number 4, which is on page 3. Starting with writing our function and defining our variable. So all these steps will be laid out for you on the final. So what we are going to do first is define the variables. A lot of times I look at the very tail end part of the question because often that's what tells me what it is I am trying to find. So that last part of the question asks, how many magazines and books can they make each day to maximize their profits? This tells me what I'm looking for as far as X and Y go. So magazines are X, books are Y, and how many can they make each day to maximize their profits? So it also tells me that I'm going to be maximizing my objective function and the units of my objective function. So X is going to be the magazines, and Y is going to be the books. So all that came from the last part of the question, magazines and books. Our objective function is going to be maximized, and what we are going to maximize has a unit of profit or money. So let's start with that objective function notation. F of x, y, making sure that we've got that memorized for the test, is equal to, and now I want to sift through the problem to see if there's anything in there about profit. I'm never going to give you extra information. You never use the information twice. So we always need to make sure that we use every piece of info in the problem one time. So do we know anything about profits or money in the problem? We know that for each magazine, they earn $3. $3 in profit. So if magazines represent X and they earn $3 per magazine, that would be 3X. $3 for every magazine. And then for each book, they earn $5. So books are Y, so $5 for every book is going to be plus 5Y. So there it is. That's our objective function that tells us how much money we're going to be making for how many books and magazines we sell. So again, a lot of times I look at that last sentence or last question in the problem because that usually tells you what you're trying to find. Our next step is writing the inequalities. Now, how many inequalities you have is going to vary with the problem. So the important thing is going to be looking for totals and using all of the information in the problem. So let's go ahead and just start reading through the next sentence. The printer can print a magazine in 2 minutes. So 2 minutes for every X, or for every magazine. They can print a book in 3 minutes. So 3 minutes for every Y, for every book. Now, that machine, the printing machine, can only run for 300 minutes per day. It doesn't care if it's making magazines or books. It can only run for 300 minutes or less. So what inequality sign are we going to need to use here? Less than or equal to 300. So this is our printer minutes. So it can run for 300 minutes or anything less than that, but if it can only run that amount, anything more, we'd shut it down. So that's our total in this inequality, the 300 minutes for printing. Now, the left side of this equation, what do we know about printing in the context of our variables? 2 minutes for every magazine and 3 minutes for every book. So 2x plus 3y. There's inequality number 1. With that in mind, see if you can write inequality number 2. So we've got an assembly machine. It can assemble a magazine in 3 minutes, so 3x. A book in 6 minutes, 6y, using our defined variables from above. And that machine can only run for 480 minutes a day. So anything less than or equal to 480. So assembly minutes. You don't have to write the units there, but that may be helpful to you as you are working through some of the other problems, that everything in that problem has the same unit. Now, at this point, after doing all of our underlining, we have successfully used all of the information in the problem, but there are 2 more inequalities that we need. Does anyone remember what those other 2 inequalities are? Can we make negative stuff? We can't. So our other 2 inequalities state that x needs to be greater than or equal to 0 and y needs to be greater than or equal to 0. You won't always need those 2 inequalities, but if you don't have any other solo variable equations, this is what restricts those variables to be positive. So let's go ahead and add that to our flow chart on the front. That when we write our inequalities, sometimes we will need x greater than or equal to 0 and y greater than or equal to 0. That's what keeps our stuff positive. The other thing that I would like you to write by these is that solo x equations are vertical lines and solo y equations are horizontal lines. That's our whole Vex Hay mnemonic device. So this will be a vertical line at 0, and that will be a horizontal line at 0. And that will help you with some of those other problems as well. And actually, folks, we're going to sidebar for a moment. I want you to go ahead and go up to number 1. And this is inequality number 1. So solo x equation, how are we going to graph that? That's going to be a vertical line at -1. Now, I did get some popsicle sticks, but I think I only have enough to, like, get us through finals. So just because I don't want anybody to, like, risk losing them. For right now, you can just use your phone or the side of your calculator to make your straight lines. So x greater than or equal to -1. If I plug in 0 for a test point, 0 is greater than or equal to -1. So teeth going to the right. So vertical line at -1 saves us a little bit of time with graphing. Now, number 2, what's a little bit odd about this one? There are 2 inequality symbols. So this is kind of like pulling apart an Oreo where you can get frosting on both cookies. So we are going to twist this apart and say that 2 is less than or equal to y, and y is less than or equal to 6. Flip that around, and we get y is greater than or equal to 2, or y is less than or equal to 6. You can break it up into 2 inequalities like that, but some students like it better to just read this as we are going to have 2 horizontal lines with shading between 2 and 6. So I actually prefer that method. I'm going to draw a horizontal line at 2, a horizontal line at 6, and then since y is between those 2 values, our teeth is going to go in between those 2 lines. So that's the only part of this problem I wanted to go through with you guys. I think you should be able to do the rest of those parts by yourself. So flipping back to our other page with the story problem. We now have all of our inequalities, so it's time to graph. Now, our graph to the right is constrained to the positive part of the coordinate plane, our positive quadrant 1, but we're going to need to choose the scale. Instead of just going off of these rough numbers that we have, to choose the scale, we are going to find our x and y intercepts. So let's go ahead and make a table for number 1. So this one is in standard form, so we're going to use the cover-up method to find the intercepts. So what happens if I plug in 0 for y? So if I plug 0 in for this y, what's 3 times 0? 0. So then I have 2x equals 300. If I divide both sides by 2, what's 300 divided by 2? 150. So there's our x-intercept. And now we do the same thing to find our y-intercept. We're going to plug 0 in for the x. So 2 times 0 is 0. So then if 3y equals 300, we divide both sides by 3. And what does y equal? 100. See if you can use the cover-up method to generate your table for that second inequality. So plugging in 0 for y, if we divide 480 by 3, we get 160. And then if I plug in 0 for x, 6y equals 480. We divide both sides by 6, and we get 80. Then for our solo variable equations, this will be a vertical line of x at x equals 0 and a horizontal line at y equals 0. So now we have enough info to choose our scales. So it looks like our lowest intercept is 80. And our highest one is 160. So what do you think would be a good scale to pick? Tens I don't know if our graph is quite big enough for that, so I would go by 20s. It is important that you choose an appropriate scale because we want to make sure that our data is spread out enough so that we can see any sketchy vertices and also just the basic layout of the data. So let's go ahead and start plotting these points. So 150, 0, 20, 40, 60, 80, 100, 120, 140, 160 would be here. So 150 directly in between those tick marks. 20, 40, 60, 80, 100. And then using something for a straight edge, you can use your phone. Line number 1. And again, labels are important, especially for me checking these term tests efficiently. So it would be helpful if you labeled your tables, your inequalities, and the lines on your graph. Now, what we have just done is graph the line. What we also need is to graph the inequality. What makes an inequality different from just an equation is we have to have shading. So we can use 0, 0 for a test point. And if I plug 0 in for x and for y, 2 times 0 is 0. 3 times 0 is 0. Is 0 less than or equal to 300? Sure is. So teeth going down towards 0, 0. Now, your teeth aren't always going to go down in the direction of 0, 0. It won't always be a bounded region. So it is important to explicitly do the test point to make sure that it matches the inequalities that you wrote. Moving on to our next intercepts, we've got 160, 0. So if this is between 140 and 160, 160 is here. And then 0, 80, if that's 100, this would need to be 80. Connecting those dots with a straight line. Can I take the test? Yeah. Using 0, 0 for a test point is 3 times 0 plus 6 times 0, 0, less than or equal to 480. It sure is. And then a vertical line at 0. Since it's x greater than, we're going to have teeth going to the right. And then y greater than or equal to 0. Be a horizontal line. Teeth going up. So we have now graphed our lines. Now we need to figure out where our feasible region or our solution shading is. I usually start at a jawline of teeth. Bottom corner's looking good. And then I just follow those teeth all the way around. Making sure I don't cross into a region that shouldn't be colored. For example, above that pink line doesn't have teeth, so I wouldn't want to color over there. And there's our feasible region, and that represents all of the coordinates that satisfy all 4 of those inequalities. So how many vertices do we have? How many corner points does this feasible region have? We'll start with the easy one. It's got 1 down here in the corner at 0, 0. So vertex number 1, 0, 0. Vertex number 2, if you're worried about reading the scale wrong, this is the y-intercept of my second line, which I did not label. So line number 2. So y-intercept of my second line would be 0, 80. Then my next easy one down here would be the x-intercept of my first line. So 150, 0. Now, we don't use all the intercepts as our vertices, only the ones that are outlining the shape of that feasible region. But folks, is there another vertex? Right here where those 2 lines are intersecting. Folks, this is what we called a sketchy vertex. My scale is large, my numbers are big. It looks like it's pretty close to being on the grid, but this is one that's floating out off our grid, not on the axis that we would want to find exactly. How we find those sketchy vertices is by using substitution or elimination. Now, we did a lot of substitution in Unit 4, Part 2. Elimination we haven't seen for a while, but it's a bit more useful when your equations are in standard form. So if we want to find that vertex, this is the intersection of line 1, this guy over here, and then line 2, this one over here. Now when we are finding the intersection point, we're concerned about the lines themselves or the equations, not the shading. So I'm going to go ahead and write that first inequality as an equation. And then I'm going to write that second inequality as an equation. Now, since these are written in standard form, the variables are easily stackable. So I would say elimination is looking a bit better for this one. So is there a way for me to get equal value and opposite signs so that my variable will cancel when we add those equations together? Or a shorter way of asking is, what can I multiply equation 1 by so that when I add it to equation 2, the y's cancel? We can multiply this one by -2. So times, times, times. So my new equation 1 will look like -4x, -6y, and -600. Add those together, and we get -x equals -120. Divide both sides by -1, and x equals 120. So similar to finding the intersection point of a line in a quadratic, once we have the x value, what do we need to do to find the y value? I'm going to have to plug it back in. Now, neither of those equations are especially friendly to plug into, but I do like it that equation 1 has smaller numbers. So let's go ahead and plug that into equation 1 for the x value. So 2 times the x value of 120 plus 3y equals 300. So let's see, that's 240 plus 3y equals 300. Subtract the 240. 3y equals 60, and y equals 20. So that is our intersection point, and that's the location of that sketchy vertex. Now what's nice is we can check ourselves graphically and see if this looks close. 20, 40, 60, 80, 100, 120. Y value is 20. Oh yeah, it's pretty much right on the money there. And that's very nice to keep in mind, because if we flipped our x and our y values around or just made some sort of crazy mistake where x was negative or x was 20 and y was 120, if I go forward 20 and up 120, that's definitely not looking like it represents the coordinates of that sketchy vertex. So that's what's kind of nice about this, is that we can use our graph to check ourselves. So then our final sketchy vertex would be 120, 20. Any questions so far? So now that we've got all those vertices, it's time to plug them into our objective function. I think this was like step 6 from the front. So I'm going to take each of these xy coordinates, and I'm going to plug them into that f of xy equation that we defined above, that 3x plus 5y. So I'm going to take 3 times the x value of the first point, and then plus 5 times the y value of that point. And 3 times 0 plus 5 times 0 is 0. 0 what? $0. That is the unit of our objective function. We're trying to find out how to maximize profits. If I make 0 magazines and 0 books, I'm going to make $0. So x and y represents what you're producing, and then what you get from your objective function is the profit from producing that amount. So 3 times 0, I produce 0 magazines and make $3 off of each of those 0 that I produce. And then 5 times 80 books. So if I only make books, we're going to get a profit of $400. Then 3 times the x value of 150 plus 5 times the y value of 0. That gives me the profits of $450. Getting larger. And then 3 times 120 books plus 5 times 120 magazines and then 20 books. And when we add those together, $460 profit. So our final step is to choose our solution and to answer the question, making sure we use proper units. So this is what we mentioned on the front, saying after you plug into your objective function, you need to state your solution in terms of the units of the problem. So we're not going to say a max of 460 at the coordinate 1, 20, 20. Because this is a story problem, we have to use units, and we have to use kind of complete sentences. For a max profit, so we're looking for the biggest amount, for a max profit of $460, they should make $120 magazines and 20 books. So we're stating our full answer, the maximized amount, and the X and Y value that gets us there in terms of the story problem, including proper units for everything. And folks, that's linear programming in a nutshell. Does anybody have any questions on any of those steps or where any of those values came from? All right, we're going to take just a quick breather and then we'll start our next section on transformations.